Good evening everyone. I welcome you all to the problem solving session of the NPTEL course on ice engine and gas turbine. I am Pradeev E. I am one of the TAs for this course. So today I have some problems on SI engine, carburetor and diesel engines fuel injection system. Let's see this problem. Determine the change of air-fuel ratio in an aeroplane engine carburetor when it takes off from the sea level to a height of 5000 meters. Carburetor is adjusted for 15:1 ratio at sea level, where air temperature is 27 degrees Celsius and pressure 1 bar. Assume the variation of temperature of the air with altitude T equal to Ts minus 0.0065 H, where H is in meters and T is in degrees Celsius. The air pressure decreases with altitude as per the relation H is equal to 19,200 log base 10 of 1 by P, where P is in bar. Evaluate the variation of air fuel ratio with respect to altitude in steps of 1000 meters on the trend. Show the variation on a graph on this one. So for this, in the previous week, we have derived this relation like AFR 1 to AFR 0. So maybe this is 1 is at altitude and the denominator is at sea level. This can be written as pressure at altitude by pressure at sea level into root of temperature at sea level by temperature at altitude. So I will assume H is equal to 5000 meters. So actually we need to find for different H, like from 1000, 2000, 3000, 4000 and 5000. I will just find for 5000. The remaining can be solved by yourself. Now to calculate temperature at 5000, I will write that as temperature at altitude, that is T at surface level minus 0.0065 H. So this is at surface level, Ts is given as 27 degrees Celsius, and that would be, okay, we can have it as 20 in degrees Celsius itself, minus 0.0065 into H is 5000. Can you calculate the temperature? Sorry, 32. It is 27 minus something. The answer is minus Okay, this answer is minus 5.5 degrees Celsius, and to write it in Kelvin it will be 267.5 Kelvin. Then similarly, for to find the pressure at the altitude, we can write this equation: H is equal to 19,200 log base 10 of 1 by pressure at the altitude. So here H is 5,000, then we will have log 1 by pressure at altitude base 10 is equal to 5,000 by 19,200. So to remove log, we will have 1 by pressure at altitude is equal to 10 power 5,000 by 19,200. Can you calculate this? Point 0.45. Actually, I am getting, sorry. Okay. PAL is 0.45 bar. This I am getting as 1.821. If I take the reciprocal, I am getting 0.549. Can you check again? Okay. So 0.549. Okay. So then we got the pressure and temperature. Now we can substitute in this one and get the AFR at the altitude. AFR at altitude is it will go AFR at sea level into pressure at altitude divided by pressure at sea level into root of temperature sea level by altitude. So this is 15. Pressure at altitude is we just calculated as 0.549 bar, and pressure at sea level is 1 bar. It is given as 27 degrees Celsius and 1 bar. So I have 1 here, and temperature at sea level is 27 degrees Celsius, and that will be 300 Kelvin, divided by temperature at altitude is 267.5. Can you calculate the air fill ratio? 8.7. So this is the air fill ratio if when the flight is when the flight is flying at an altitude of 5,000 meters. So similarly, we can substitute for 1,000, 2,000 meters and then find the other values. Yeah, air fill ratio is actually what is air fill ratio? Mass of air divided by mass of fuel. It can be mass rate or directly mass per cycle. So both will be kg of air by kg of fuel. So there won't be any units. It is a ratio. Fine. Yes. We started with 5,000. Yeah, we need to calculate in steps of 1,000. So ideally we should calculate at h equal to 1,000, 2,000, 3,000, 4,000 and 5,000. I've just calculated for the last value. You can calculate for the other things. Next problem. A 4-cylinder 4-stroke diesel engine develops 100 kilowatt at 3500 rpm. Its brake specific fuel consumption is 180 gram per kilowatt hour. Calculate the quantity of fuel to be injected per cycle per cylinder. Specific gravity of the fuel may be taken as 0.88. Volume of the fuel. So this is the answer. So can you mention how we can solve this problem? So engine power is given, the speed of the engine is given, BSFC or the brake specific fuel consumption is given in gram per kilowatt hour. We need to calculate the quantity of fuel to be injected per cycle. Okay. So first we can calculate the energy per cycle for the engine, like mechanical energy or the brake energy. So it is given, it develops 1000 kilowatt at 3500 rpm. So power is equal to 1000 into 10 power 3 joules per second. And with rpm, so speed is 3500 rpm. So if you want to have it, so this can be written as 3500 divided by 60 revolutions per second. And we know of, since it is a 4-stroke diesel engine, for every 2 revolution we will have 1 cycle. So this can be written as 3500 by 2 into 60 cycles per second. Now to calculate the brake energy per cycle, and also that this is a 4-cylinder engine, so that means power per cylinder is 25 into 10 power 3 joules per second, because only with 4-cylinder we were getting 100 kilowatt, so for each cylinder we will get only 25 kilowatt. And speed is given. From speed we have calculated the cycles per second. Now we can calculate the brake energy per cycle. So how do we get, divide this 25,000 joule per second divided by something cycle per second will give me joules per cycle. So brake energy per cycle is 2 into 5, 25 into 10 power 3 divided by 3500 by 120. Can you calculate this? This will be joule per cycle. Okay. So this is 857.14 joules per second. So this is the brake energy that we have got. And we have something mentioned as like the brake specific fuel consumption, brake BSFC, is 180 gram per kilowatt hour. So actually kilowatt hour is also is a unit of energy. Just that it is not in joules, we can convert it to joules. And for every joule of brake energy produced, we know how much gram of fuel has to be given, and that is what BSFC utilizes. So to convert this to in terms of joules, we can write this as 180 gram. So first we'll put 1 kilowatt hour. 1 kilowatt hour is 1000 joules per second hour, right? So or 1000 watt hour So this is 1000 joules per second into hour, and we know in 1 hour there is 3600 seconds. So this will be 3.6 into 10 power 6 joules, that is 1 kilowatt hour. So if you rewrite BSFC in a different unit, you will have 180 divided by 3.6 into 10 power 6 gram per joules. Now we need to calculate the quantity of fuel to be injected per cycle per cylinder. So that means we need to have gram per cycle, right? So how do we get? We know how much joules of brake energy comes from every cycle, and we know how much of grams to be given to produce every single 1 joule of work output. So then we multiply both, we will get the fuel quantity per cycle. This is 857.14. This is into 80 by 3.6 into 10 power 6. So how do I get, like, how do I confirm this is joule per cycle, and this is multiplied by gram per joules? So I will have joules and joules get cancelled, then finally my result will be in gram per cycle. Can you calculate this? One 1042 grams. We want a unit in cc, then how do we convert? So we know specific gravity. What can we do with that? Okay, so how do I put? So specific gravity is given as 0.88. What is volume by mass? Sorry, specific volume. But we know only specific gravity, no? Yeah. What is specific gravity? Density? Density of what? Liquid. Then what is density? What is the difference between density and specific gravity? No, no, no. But the question is specific gravity. And there is no unit given. It's only written as 0.88. Okay, specific gravity of a liquid is is density of the liquid is divided by density of water. What is density of water? 1000 watt units. Kilogram per meter cube, or it can be written as 1 gram per cc. So if you take a 1 liter water can, how much it will weigh? It will be 10 kg, 1 kg, 0.1 kg. 1 liter of water can, water alone, how much it will weigh? 1 kg. Yeah, pure water at standard conditions will be 1 liter of water will be 1 kg. So then from this you can convert this one. So if you want meter cube, then meter cube is 1000 liters, so it will be 1000 kg. And here it's also, we know it is 1000 ml. 1000 ml is 1000 grams, right? So 1 ml is 1 cc. So that is 1 cc is 1 gram. So that is 1 gram per cc. So if specific gravity is 0.88, then using this thing we know specific gravity of the fuel is 0.88 gram per cc. So if you want to, in your problem, if you had meter cube and kg and all, then you can directly write it as 880 kilogram per meter cube and then solving, start solving. But now we have in terms of grams and the result is in cc. So then I take it as gram per cc and then try to proceed further. So now I know fuel quantity in mass, so that is 0.042 gram. How do I calculate quantity in volume? Like, yeah, in volume. Fuel quantity in cc is equal to, I put some mass, the mass that I got, and then divided by gram per cc or density. So here numerator unit will be gram, denominator will be gram per cc, then I will finally have cc. So mass is 0.042 and density is 0.88. Can you calculate this? Point zero, again 0.042. So it is 0.487. I think we should have got here 0.428 gram. We missed the 8, so that is okay. So we have got something closer to the answer. So you have any questions? Okay, if there are no questions, I will move on. Sorry? No, specific gravity we saw, no? It is density of the liquid by density of water. It is normalized to the density of water. Yeah. Normalized means divided by the density of water. So that means we are just comparing how different it is from the density of water. If 0.88 means it is 88% of the density of water. If some specific gravity of some liquid has say 2, then that means it is twice dense as water. Yeah, for water 1 cc is 1 gram. So Yeah. So this 1000 ml is 1000 gram, right? So then we know what is 1 ml. 1 mm in cc, sorry, 1 ml in cc. 1 ml is 1 cc. Yeah, so then 1000 ml is 1000 cc is 1000 gram, then 1 cc is 1 gram. Okay. Then we go to the next problem. Six-cylinder four-stroke diesel engine develops a power of 200 kilowatt at 2000 rpm. The BSFC is 0.2 kilogram per kilowatt hour. At the beginning of injection, the pressure is 35 bar and the maximum cylinder pressure is 55 bar. The injection is expected to be at 180 bar and the maximum pressure at the injector is set to be about 520 bar. Assuming the following: CD of injector, specific gravity of fuel, atmospheric pressure, and assuming effective pressure difference is average pressure difference over the injection period, we have to determine the total orifice area required per injector if the injection takes place over 16-degree crank angles. So a six-cylinder four-stroke diesel engine is given, the power and speed is given, DSFC is given. So with these things we can calculate the fuel quantity required for one cycle, in one cylinder. Then we know the quantity. Now the pressure difference is given, like the in-cylinder pressure varies from 35 bar to 55 bar during injection, and at the same time at the upstream of the injector the pressure starts from 180 bar and ends at 520 bar. So that means the across the orifice the pressure difference is varying. Like say this is an injector and this is a cylinder. So this is injector and cylinder. The fuel pressure varies from 180 bar to 520 bar, whereas in the cylinder it varies from 35 bar to 55 bar. So based on this we can find the average pressure difference, and that can be taken as effective pressure difference for the calculation, so on. And with pressure difference we can calculate the velocity across the orifice. With the velocity is 2 delta p by rho, this equation. And with this we know the velocity and we know the total quantity calculated earlier using BSFC power and all. And then with these two relations, like we know m dot is rho a v, and everything else will be known, only area is unknown. We can calculate the area, orifice area. So to first start with, we calculate the quantity. Power is 200 kilowatt, and that is 200 by 6 cylinder. Since it's the 6 cylinder engine, it is, we put by 6, and that is 33.33 kilowatt per cylinder, and this is at a speed of 2000 rpm. So with 2000 rpm, to calculate the cycles per seconds, we know it is 2000 by 2 into 60. So this will be cycles per second. 16.67, right? Yeah, 16.67 cycles per second. So now we can calculate joules per cycle. Energy per cycle is 33.33 into 10 power 3 joules per second divided by 16.67 cycles per second. Can you calculate this? Sorry, 2001.79 joules per cycle, right? Yeah, joules per cycle. Uh, so just a minute, I will come back some urgent. Oh, sorry. Yeah, so we have found the amount of energy, break energy. Next we can calculate the fuel quantity needed for one cycle. So here the BSFC is given as 200, so it's 0.2 kilogram per kilowatt hour. So this will be 200 gram, and to convert the kilowatt hour we saw it is 3.6 into 10 power 6 joules. So BSFC is 200 by 3.6 into 10 power 6 gram per joule. Now to calculate quantity or MF in terms of gram per cycle is equal to 2001.79 into 200 by 3.6 into 10 power 6. Can you calculate this? So this comes to be, say, MF is 0.1112 gram per cycle. Now we know delta P. So m dot F is rho A V. V can be calculated using so V is under root 2 delta P by rho, all for the fuel, and this is only m dot F. So we need to know the time also, and then finally find the V. So first we can start with delta P effective. So delta P effective is, as I said here, it is fuel pressure is initially 180 bar and then 35 bar at the cylinder. So the initial delta P across the orifice will be 180 minus 35, and we need to take average of the initial and final delta P. So initial delta P is 180 minus 35, and similarly final delta P is 520 minus 55. So finally the fuel pressure will be 520 bar, whereas the cylinder pressure will be 55 bar. So it is 520 minus 55. 520 minus 55. So average of this delta P will give the effective delta P. So this is 305 bar, and now we can calculate velocity, that is 2 into 305 bar, that is 305 into 10 power 5 divided by rho, and rho is specific gravity is 0.85. we need to have in SI units so that finally we will get in meter per second, and specific gravity is 0.85, so the it should be 850 kilogram per meter cube. Now we can calculate the velocity across orifice. So velocity is 267.89 meter per second. So this is the velocity. Now we know the mass flow, total mass that has to be flown, but we do not know the mass flow rate. So to find the rate, we are given the crank angle for which it is injecting. So that is 16-degree crank angles, 16 degree crank angles. And with the 16-degree crank angles and 2000 rpm, we will be able to find the time taken for injection. What do you think? So 2000 rpm means 2000 into this is 2000 by 60 rotations per second, and to get it into crank angles, every rotation will have 360 degrees. So this is 2000 by 60 into 360 crank angles per second. So this we will have 6, so this will be 12,000 crank angles per second. And it was given as delta, we write crank angle degrees as CID, and that is 16 degrees, and so that means delta T will be delta crank angle degrees divided by 12,000. So 12,000 is crank angle per second, so finally crank angle will get cancelled, and then we will have in seconds. This is 16 by 12,000. Hello, are you audible? Am I audible? That is 1.33 into 10 power minus 3 seconds. Now delta T is known, so rate is m dot f is m total m by delta T, that is 0.1112 divided by 1.333 into 10 power minus 3. Can you calculate this, please? Okay, so this is 83.42 should be gram per second, because we had just confirm. Yeah, so this is 83.42 gram per second. Yeah. So now we have got m dot f. Next is to calculate OAD. Yeah. So this is equal to rho AD. So assume we have rho in gram per cc. No, I think it's better we have everything in seconds. So this will be 83.42 into 10 power minus 3 kilogram per second. M dot f is equal to rho AV. Have we given some orifice? Yeah, CD for injector is given. So that is 0.75. That means we should have a CD term here. CD into rho AV. So this is 83.42 into 10 power minus 3 is equal to series 0.75. Rho in terms of SI units is 850 into A, and velocity is 267.89 meter per second. So area is equal to 83.42 into 10 power minus 3 into 267.89 divided by 0.75 into 850. Can you calculate it, please? .035. What is the unit? should be meter square. Delta CD. CAD, crank angle degrees. But I think we are missing some 10 power minus 3 or something somewhere. Oh, sorry, I think here area is equal to 83.42 into 10 power minus 3, and all other numbers should be in the denominator, right? All or with the a. 0.75, 2367. Since I wrote this number in the second line, I thought it is 4 point. I think this is what. Yeah. So answer is 0.487 into 10 power minus 6, both are same. Sorry, what is CD, CAD? Crank angle degrees. Yeah, I think you can also just write CAD. Yeah, CAD is correct. Or sometimes CAD in some engine literature you will also see it as crank angle duration. Okay, anyway. You have any other questions in this problem, or we can move into? No, this is diesel fuel injector. So we will have an injector, right? So there will be orifice here, and summation of all the areas is this one, 0.486 4876 into 10 power minus 6. So if we have, we can decide to have 3, 5 or 7 holes, and then each hole will have different diameter. So for example, we can also calculate what kind of diameter we are talking about, assuming we have say 6 hole injector. So area is 0.4488 into 10 power minus 6. So area is 0.488 into 10 power minus 6 meter square. If we have say 4 number of holes, holes is sorry 6. Then area can be written as n into pi by 4 d square, right? So pi by 4 d square is area of single hole. Now it is pi by 4 d square. Now this is 0.488 into 10 power minus 6 is equal to 6 into pi by 4 into d square. So d is 4 into 0.488 into 10 power minus 6 divided by 6 square. Very good. And calculate d. 1.6 into 10 power minus 4. This should be in meters, right? But I am getting 3.22. I am getting 3.2. Oh, everyone is getting different answers. 4.6 into 10 power minus. Okay, so this has come to twice. This has come 1. So if this is the case, so then it is 0.32 mm, right? Yeah. This is even bigger for a diesel engine. Modern common rail diesel engine will have say this of diameter of 0.14 mm or 0.17 mm in that range. So that means it's 140 micrometer. You can think of how small it will be. I think hair is 200 micron or something. At least in the order of the diameter of hair. So such precise holes has to be drilled for the injector, and then if there is some variation in say if, for a 6-hole injector, if there are 6 holes at different diameters, then the engine performance will be very bad. So it has to be very precisely machined. And even a small dust in the diesel can clog this injector holes. So we should have proper filters, and there will be some different many stages of filtering before it can go into this hole, before the fuel can go into this hole. Okay. Any other questions? Yeah, injector, that nozzle hole where the fuel flows, like this hole. Yeah, yeah. Injector can have many holes. Like some old injectors used to have only 3, and modern injectors have 7, 8 holes also. And Hemant has asked what is orifice area. So that means so the injector will have a needle like this, and then a stem or body, and the fuel will be supplied through this by some other means. Okay, fuel will be there will be holes here. So once the needle is lifted, then fuel flows in and then comes out through this orifice holes. So this hole where the fuel gets injected from the injector to the cylinder is called orifice. and the total area of the all the holes is called orifice area, and that has to be some value like 0.488 into 10 power minus 6 meter square to satisfy our condition, like to satisfy the engine with the 200 kilowatt 6 cylinder with a BSFC of so and so, and when the pressure difference across the orifice is like 305 bar and all, then we need to have total orifice area of 0.488 into 10 power minus 6 meter. And assume if we are going with six holes, then the diameter has to be 0.32 mm. Any other questions? So a regular diesel injector will have say needle like this, and there will be a projection at some point, and this will be the outer body, and fuel comes to this fuel comes to this cavity using another, and this will be under spring action. So initially the spring will be pushing the needle downwards, and that will be this region will be closed when it is spring action is there. And when fuel at high pressure comes to this chamber, and because of this change in area, like this area is, this diameter will be say some B0, and this diameter on the needle will be B1, which will be higher, little higher. So that difference in diameter will give a area, effective area for the fluid pressure, and that will cause a upward force. And when it overcomes the force given by the spring, then the needle will start to move upward, and when it moves upward, the hole at this surface will get uncovered, and then this fuel will enter through this and comes out of the hole. So there will be, if you see from bottom, there will be say 6 holes like this, 6 or 4 holes. I drawn 5 holes here. Any other questions? This will change according to cylinder area. It will not change according to area, but so based on the cylinder capacity, say if we have 500 cc engine, or say 500 cc per cylinder, so we want to because we have every injector for every cylinder, we need to talk about the air quantity, fuel quantity, everything per cylinder. So if you have 500 cc per cylinder, and if it is a naturally aspirated engine, then we can calculate how much of air theoretically we can get in. Mass of air will be say something like 2 gram per cycle. Now to burn this 2 gram, we can provide some amount of fuel at maximum. So we have seen some air fill ratios earlier. So generally for diesel engine, air fill ratio will be maximum of say 20, but the stoichiometric air fill ratio will be around 15 is to 1. But it has to just come out of the injector and then start mixing, and then everything has to be utilized, all the air has to be utilized. So we will give some margin of say 20, uh, though the stoichiometric air fill ratio is 15, we can go up to only 20, because some air in the cylinder will be unused. So we will have say with air fill ratio 20, and then the mass of air that can be taken in is 2 gram per cycle. Then based on this, we can calculate some mass of fuel that can be given inside the cylinder for every cycle. So this is some say to 20 milligram. Then for this 20 milligram and the pressure for the at which the fuel can be reached pressurized. Based on that, we can do this calculation and then find the orifice area or the orifice area, and then based on number of holes we can calculate the diameter of the hole orifice. Now this can change if the 500 cc is, say, now has become 1000 cc. I want to design a 1000 cc engine. Again, the m dot a will change, or mass of air per cycle will change. Instead of naturally aspirated engine, I have a turbocharged engine where I compress the air before it enters the cylinder. So now, earlier it used to enter at, say, 1 bar. Because of some losses it can be 0.9 bar or 0.95 bar. Now if I turbocharge, it can go up to, say, 4 bar maximum. Then 4 bar means I will have around 4 times air available. So earlier I had 2 gram per cycle. Now I can have 8 gram per cycle of air. Now for 8 gram per cycle of air, say with 20 airfill ratio, I can calculate what should be the what could be the fuel that can go in and burn. And that milligram with this and all the pressure difference and all I can calculate. And if the pressure I can raise the fuel pressure that I can go up to, say, 1000 bar instead of this 500 or 300 bar that we have seen, then orifice area can be lesser. So these are the factors that affect the orifice area. So it's not only cylinder area. Cylinder area, I think it will affect the CC, provided the stroke is constant or not, and there are many factors which affect. Any other questions? Then we can move on to the next problem. Closed type injector has a nozzle orifice diameter of 0.494 mm, and the maximum cross-sectional area of the passage between the needle cone and the seat is 1.75 mm square. The discharge coefficient for the orifice is 0.85 and the passage is 0.8. The injector pressure is 175 bar and the average pressure of charge during the injection is 25 bar. When the needle cone is fully lifted up, the injection pressure is given. Calculate the volume rate of flow per second of fuel through the injector and the velocity of jet at that instant. Density of fuel is 850 kg per meter. So what they have given is there is a injector. I mean, everything together will be injected. We can call this as line pressure, and that is given as 175 bar, and that is given to a seat area, and then it goes to the cylinder. So as I drew here, so this pressure is 175, or this can be like a line pressure, and then this in this region, this is seat area, and to go for the fuel to enter the seat area, it has to go through a fine passage. So this passage will cause some pressure difference, so that is why it is modeled separately, and the coefficient of discharge everything is given. And in the seat area, from the seat area, again through the orifice, it comes out of the out to the cylinder. So that is what we have, say, 3 volumes and then 2 interfaces. The first interface, cross section area, this cross section area is 1.75 mm square, and CD is given as, so I will write it as A1 CD1. CD is given as orifice and passage is 0.8, and similarly here area 2 or the orifice area is okay, we are based on diameter we can calculate. It is D2 is 0.949 mm, but number of orifices is not given. Maybe it is a single hole injector. And then CD2 is 0.85. And at cylinder it is given as 25 bar. Density of fuel is 850 kilogram per meter. Now we need to calculate the volume rate of flow per second of fuel through the injector. So how do we solve this? We can start writing orifice equation for different interfaces. So we can consider the first orifice, this one, and this is second orifice. So Q1 from the line pressure to the seat area, we have 2 delta P by rho, and that is 2 into line pressure. So this I write as P injection minus P for the pressure of the area, and then density of fuel. This is Q1. Similarly, Q2 can be written as 2 into P minus P cylinder divided by rho. So that is this interface. Now at steady condition, both has to be same, right? So that means Q1 is equal to Q2. Then we write this as 2 P injector minus seat area pressure is equal to 2 P minus P cylinder divided by rho. Now we can remove the under root. We can root 2 rho, everything will go. We will be left with P injector minus P is equal to P minus P cylinder. Now we know P injection is 175, and then P cylinder. Okay, then we can write P is P injection plus P cylinder by 2. That is P injection is 175 plus 25 by 2. Okay, I think we missed something important. We missed the CD value. What we have calculated is just velocity, sorry. So velocity 1 is 2 delta P by rho. Similarly, V2 is 2 delta, okay, I will write 2 into P injector minus P by rho. This is 2 into P minus P cylinder. Now M1 is CD into rho AV. Similarly, M2 under is CD into CD2 1 rho A2 V2. So now we know rho is same. So at steady state m dot 1 equal to should be equal to m dot 2. Then we will have CD1 rho A1 V1 is equal to CD2 rho A2 V2. Now CD1 is 0.8. Rho will get cancelled anyway, and area 1 is 1.75. It's better we can have both side mm and then they get cancelled. And velocity is 2 into 175 minus pressure divided by, so this should be in Pascal, so I'm converting bar to Pascal by multiplying by 10.5, and density is 850, and here it is 0.85 into area is pi by 4 d square. D is 0.949 square into 2 into P minus 25 by 850 into 10 by 5 by 8. Can you calculate P? Will be able to calculate or will break down? So taking only 0.8 into 1.75, that will be 1.4 into 2 into 175 minus P 10 power 5 by 850, the whole root is equal to this is 0.601 into 2 into P minus 25 10 power 5 by 850. Now next we have 2.3294 into 2 175 minus P 10 power 5 by 850 root is equal to 2P minus 25 10 power 5 by 850. So now I can take square on both sides. Then I will have 2.3294 square and others will be the same. Now I can cancel 850 10 power 5 2 also. We will left it only this term. So 2. This square is 5.426 175 minus P is equal to P minus 25. Now this is 5.426 into 175 minus plus 25 is equal to, here P coefficient will be 1 plus 5.426, so that will be 6.426P. So P is 5.426 into 175 plus 25 divided by 6.426. So can you calculate this? We can cancel root on both sides. Yeah, we can cancel, no? We will take square, so then everything will get cancelled. Like we cannot cancel when there is a non-square term like this, like a non-root term. So that is why I am taken square, and then only this 2.32 will have a square. Other terms root will be gone. Yeah, 151.6. I also got this 151.65 bar. Hemant, you can check once. Anyway, it should be between, we know there are 3 chambers, and then one chamber on the left hand side has 175 bar and rightmost it has 25 bar. So in between should be somewhere in between 175 and 25. It cannot be out of this. So I'll just give some time for him to find. Yeah, okay. So 151.65. Now we need to calculate the volume flow rate. Volume flow rate is Q is equal to CD into CDAV. Say we will have 1 all 1, but I think we need to calculate the velocity at the second step. So better we write Q2 equal to CD2 A2 V2. Q2 is what we need to calculate. CD2 is 0.85, and this is pi by 4, 0.949 into 10 power minus 3 the whole square into velocity. Velocity is I think velocity we can calculate separately. So this is 2 delta p by rho, and that is 2 into it is 151.65 minus 25 bar of the cylinder into 10 power 5 divided by 850. That is V2. Okay, 163 meter per second. Now we put in Q2. Q2 is 0.85 into pi by 4 into 0.949 into 10 power minus 3 square into V2 is 122.6. V2. 1.038 into 10 power minus 4 units. Meter cube per second. So we calculated volumetric flow rate, and we had everything in SI units, that is meters and all. So we got meter cube per second. So any questions? This pressure is that intermediate pressure between the line pressure and the cylinder. So as I mentioned here, this region, can you see this? Yeah, near the block diagram, the center one, seat area. Yeah, seat area. We call it seat area because that is where the orifice is covered by the needle. No, it is seating on that orifice. If there are no more questions, we can move on to the next problem. A 6-cylinder diesel engine produces 100 kW at 1500 rpm. The specific fuel consumption for the engine is 0.3 kg per kilowatt hour. Each cylinder has a separate fuel pump, injector and pipeline. At the beginning of effective plunger stroke of one fuel pump, the fuel in the pump barrel is 4 cc. Fuel inside the injector is 2 cc and fuel in the pipeline is 3 cc. If the average injector pressure is 300 bar and average pressure of charge during the injection is 40 bar, calculate the displacement volume of one plunger per cycle and power lost in pumping fuel to the engine for all cylinders. Specific gravity of fuel is 0.9 and the fuel enter the pump barrel at 1 bar. Coefficient of compressibility of fuel may be taken as 80 into 10 power minus 6 per bar. So, for 6-cylinder diesel engine is given with the specific fuel consumption. So that means we can calculate the fuel quantity needed for every cycle and for every cycle, every cylinder. Now, it is given that this fuel pump, which will have a plunger arrangement, will have a long line and then goes to the injector. So I'll just draw the injector like a cone, and this will have a port like this, so fuel can go inside here. Now the plunger, this is a plunger, and that will be driven by a cam. And when it's in its effective stroke, this point to this point, the volume that is given is the fuel in the pump barrel is 4 cc. This is 4 cc, and here it is 2 cc. In the pipeline it is 3 cc, and inside the fuel, like here, it is 2 cc of fuel is inside. So in total we can see that 4 plus 3 plus 2, that is 9 cc of fuel is in the system. And average pressure is given that injection pressure is to 300 bar, and so we can write delta T average is 300 bar minus the charge pressure, at this point it is 300 bar, but in the cylinder it is 40 bar average. So delta P is 300 minus 40, that is 260 bar. 260 bar is the pressure across the orifice. Now we have to calculate the displacement volume of one plunger per cycle and power lost in pumping fuel to the engine. So we can start by calculating the quantity of fuel that is needed. And so how do we start? So that is power per cylinder is 1000 divided by 6. That should be 16.6. 16.6 7 into 10 power 3 joules per second. Then we know specific fuel consumption is 0.3, or I would write it as 300 gram per kilowatt hour. So to write the kilogram, that kilowatt hour, we can write 300 by 3.6 into 10 power 6 gram per joule. Now if you multiply these two, we will get the grams needed for every second we'll get, right? Yeah. But before that we can also calculate the cycles per second. So since it is running at 1500 rpm, it should be 1500 by 120, that is 12.5 cycles per second. So with these two we get energy per cycle is 16.67 into 10 power 3 divided by 12.5. That is 1.336. So 1333.6 joules per cycle. And multiplying this energy per cycle with the SFC, we will get grams per cycle. So fuel quantity per cycle is equal to 1333.6 into, this is 300 by 3.6 into 10 power 6. It is 0.111 gram per cycle. I hope you are following, because this is some third time we are doing this calculation. Now specific gravity is given, so we can calculate the quantity of fuel in terms of cc. So specific gravity is 0.9. That means density is 0.9 gram per cc. So fuel volume per cycle is equal to 0.111 divided by 0.9. It is 0.123 cc per cycle. So this much of cc of fuel has to be given in. And first we were asked the displacement of the plunger. So we need to calculate the displacement volume of one plunger per cycle. So there is a compressibility factor given, and we know that this much of fuel has to be delivered. So compressibility factor says delta V by V for a given pressure. Now say this is V final, and I think there won't be any much difference. So we can write V initial minus V final by V either initial or final. So this can be final, and then pressure we can take say 300 bar because that is where it is injected, and we have here. Then finally Vi will be almost same as Vf. So that means we can take this as a volume displaced by the plunger. Okay. Now we need to calculate the power loss. So the compressing work done is, so fuel compression work is equal to P2 minus P1 into delta V. So now to calculate delta V, we need to use this one. K is equal to delta V by V divided by rho, and here the total volume is 7 cc or 9 cc. So then we have this K is 18 to 10 power minus 6 is equal to delta V by 9 divided by this is pressure, that is 300 bar, 300, and this is given in 18 to 10 power minus 6 per bar. So on the right hand side we can have it is it in bar itself. So delta V is equal to 80 into 10 power minus 6 into 300 into 9. When you calculate delta V, 0.21 cc. So 0.216 cc of fuel has to be first the plunger has to move by this one, only then we will get 300 bar. Okay, and then after that we need to supply 0.123 cc. So that means total displacement is 0.123 plus 0.216. That is 0.339 cc. So this is the displacement, total displacement by the plunger. Now we need to calculate the work done, work lost in the compression work lost. So that is P2 minus P1 into delta V, and that is 300 minus 1 bar into delta V is 0.216 cc. So we need to have this in meter cube. So cc, converting cc to meter cube, we have to multiply by 10 power minus 6. And here it is in 10 in bar, so we will have 10 power 5. So this is 299 into 10 power 5 into 0.216 into 10 power minus 6, and calculate WS. No, it's not kilowatt, it is joules. So we had pressure here in pascals, and here we had meter cube. Now, so that means Pascal is Newton per meter square into meter cube. We will have, so this is basically work done. So we will have Newton meter. So this is for one cylinder alone. Now, if you want to see for 6 cylinders, W 6 okay, 6 into 6.45, and that will be some joules per cycle, and we need to calculate the work done. So I mean power loss. So power loss is 26 into 6.45. So far we had it in per cycle. This is 38.7 joules per cycle. So we had it in per cycle. Now we know it is running at 1500 rpm. That means 12.5 cycles per second. So then we can multiply this with 12.5 to get in joules per second. Can you calculate it? 483.7. So approximately 484 joules per second, or this is 484. So this much of power is lost in pumping the fuel for all the 6 cylinders. Do you have any questions in this problem? Sorry, pressure? Average pressure across the orifice. So I think we didn't use it anywhere. So across the orifice, what is the average pressure? So like here in this region the average pressure is 300 bar, and this region like in the cylinder or the in the downstream of the orifice the average charge pressure is 40 bar. The cylinder pressure is called as charge pressure because we call it as charge coming in and going out. The fresh charge air is called as charge pressure. Average charge pressure is charge is air plus fuel, or it can be only air. So in SI engine it is air plus fuel. In CI engine it is only specific fuel consumption. Sorry, 10 power 6. We calculated earlier, no? So we have some gram per kilowatt hour. So I want to calculate the kilowatt hour, convert the kilowatt hour to joules. So 1 kilowatt hour, I can write it as 1000 watt hour. Okay, and this 1000 watt hour is 1000 joules per second hour, and 1 hour is 3600 seconds, right? So I have 1000 into 3600 joules per second into second. So finally I will have 3.6 into 10 power 6 joules. This is 1 kilowatt hour. Okay, any other questions? Okay, if you have no questions, you can move on to the next question. The heat given to cooling medium in a IC engine is about 50 to 60%, 30 to 40%, 10 to 20%, 60 to 70%. 50 to 60%. This is 30 to 40%. To uh, to remember it quickly, we can say the fuel energy is converted to work plus coolant heat plus exhaust heat. And say here if I put 100 joules here, that will go 33.3 joules here and 33.3 joules here and another 33.3 joules here. So everything will be like one third, one third, one third. So work will be like one third. So that means efficiency will be around 33.33 generally, and coolant heat will be like another 33, and exhaust will be another 33. So here we have to choose 30 to 40%. Radiator is provided to cool the jacket water, pressurize the cooling water, provide additional water flow, none of the above. Yeah. Thermostat is used in radiators to control the velocity of water, control distribution of water to various cylinders, control the water temperature, or control the pressure of water. Water temperature. So thermostat will be like a mechanical switch which will open after reaching certain temperature. Say it can be set to 70 degree or 80 degrees Celsius. When the coolant water becomes more than 80, it will open up, and then the water will flow through the radiator and come back. Otherwise, it will be stayed only within the engine. As the compression ratio increases, there is a large increase in heat rejection, large decrease in heat reduction, marginal increase in heat rejection, marginal reduction in heat rejection. Marginal increase in heat rejection. Actually, there will be a large increase in heat rejection. Spark timing other than NBT results in less heat rejection, more heat rejection, no effect on heat rejection, none of the above. Sorry, MBT is maximum brake torque. So here, if you keep changing the spark timing and then measure the torque. say this is TDC, and this is a 5 degrees crank angle before TDC, and this is another 5 degrees crank angle after TDC. So the MBT or the torque that you measure will be maximum at certain point and then start decreasing, and this point is called MBT spark timing or MBT point. So that means the it will not be a TDC, because in motorcycle we know the combustion is instantaneous, and that is why when we have the combustion at TDC, at the minimum most volume point, you will have more work output. But in reality, there will be some combustion duration that happens. Combustion cannot be instantaneous. It will take some 20 degrees or 40 degrees crank angle. And so we need to and spark timing is the indicator of the initiation of the combustion. So if you have put the spark at say 5 degrees before TDC, yeah, if you put 5 degrees before TDC, then you will have ignition delay, and then the combustion starts, and the main combustion will happen at a little after TDC, and then the pressure will be also very high just after TDC, and then because of which we will get more power output or more torque output. But if you advance or retard, like if you keep on advancing more, the pressure will start rising even before TDC. So that means while compressing while you are compressing, while the TDC is the piston is moved up by the flywheel inertia, you are putting fuel and you are burning while it is moving up itself. So that means because of the combustion pressure, you have to put more work for compressing. So that is not advantageous, and because of which the overall torque output will be lesser. And similarly, if you keep on retarding, the combustion will start very late. So like motorcycle, we have at TDC and then we have more efficiency. And but what will happen if you keep retarding the timing? The combustion will start late, and then you will have less time for expansion or less crank angle for expansion. So that means the remaining the at exhaust valve opening, the pressure and temperature of the gases will be still higher because you didn't expand well, and because of which finally you will have less torque out. So there is certain point of crank angle at which if you give the spark timing, you will get the most torque out. So that is called MBT timing. And so if you go later than the MBT, then obviously you will have more heat rejection because you didn't have good expansion time. And similarly, if you go before also, uh, you will have the same heat rejection, like you will have more heat rejection. And so that is why it is more heat rejection. There is some problem in the equation. So more heat rejection. Next one, I hope this is clear. Do you understand this MBT? Okay. So, hmm, yeah. So this is a motoring curve. Okay, and this is crank angles and this is pressure. And if you want to draw in pressure volume, it will be a just something going down, and while expanding, the pressure would have dropped because of the losses. At around TDC, you will have very high temperature and pressure, and this because of high pressure, you have some gas leaking through the crevice volume and goes to the crankcase. That is one loss, and then because of high temperature you will lose heat to the wall surrounding, and because of that the pressure, the compression pressure will be little lesser than the expansion pressure, or compression pressure, expansion pressure will be little less than the compression pressure. Now if when you have combustion, say assume you have a spark timing at TDC, the till that point the pressure will be the same, and after which there will be some ignition delay, and then there will be combustion, and then it comes like this. The pressure will rise and fall like this, and that means the effective combustion has happened only later, not at TDC, right? But if you have a spark timing where uh, you have a spark here, there is a ignition delay, and then you slowly it raised, and then went higher, and then came like this. Now the most of the combustion happens just after TDC, right? Because of this, and there is a difference between this curve and the green curve, right? In green curve, at this point, at exhaust valve open, you still have high pressure. You didn't take the work output from that combustion gases. But in red curve, you have wisely chosen the timing of combustion such that at the end of at the time of exhaust valve opening, you have already expanded all the gas, and then uh, you have converted it to piston work. So based on the start of combustion, you get different torque output. Yes. And similarly, if we go too early, like if you start the combustion here, then your peak pressure, your combustion will start even here and then expand like this. So that means even before TDC, you have reached the maximum pressure. So all while you are compressing, when you are supplying flywheel energy to compress the gas, that time itself you started combustion, and then there is more and more pressure, and there is more resistance for you to compress. So because of that also, you cannot have maximum power or rate torque, and that is why there is an optimal there. Okay. Uh, I hope there are no more questions. Then direct system of cooling air is one which cooling water flows by gravity. Hot water is continuously cooled and circulated. Hot water is simply discharged. Water is allowed to evaporate in the cylinder bracket. Cooling water flows by gravity. So this we should have seen in the theory class. In evaporate cooling systems, the heat absorbed per kilogram of coolant air is. So when you have evaporative system, the latent heat of the coolant uh, matters. Pump used in the forced cooling system is normally piston pump, gear pump, vane pump, centrifugal pump. So gear pump is used for oil, and sometimes vane pump is also used for oil. But and piston pump is used for fuel, as we saw earlier, like plunger and parallel. Advantage of liquid cooling system is dependent only on water supply. Um, Power absorbed by the pump is considerable, even cooling very cheap. So dependent only on water supply is not an advantage, it is a disadvantage, and power absorbed by the pump is considerable, it is also a disadvantage. Even cooling is an advantage because you can route the water channels accordingly finely that you get even cooling everywhere, and it is not cheap as well. Limitations of air cooling systems are applicable only to large engines. Cooling is fast, higher working temperature compared to water cooling. all of the above. So applicable only to large engines is not correct, because only for small engines you can have air cooled engine, air cooling system. Cooling is faster, and again that is not the true, and higher working temperature compared to cooling is correct. Sorry, yeah, C is right. The main purpose of the thermostat in an engine cooling system is to allow engine to warm up quickly, prevent the coolant from boiling, pressurize the system, indicate to the driver the coolant temperature. No, actually it is to allow warm up quickly. That means when it is cold, it will not circulate the coolant, so the temperature will keep on going up, and then once the temperature has reached, then the thermostat will open and the flow starts. So it will help in warm up of the engine quickly. The radiator cooling tubes are generally made of copper, brass, plastic, rubber. Out of these, copper seems fine. Nowadays, aluminum is also used. Water circulation in a thermosiphon cooling system is due to conduction currents, gear-driven water pump, change in density of water, belt-driven water impeller. So, for siphon, it is because of the change in density of water. Main purpose of fan in a liquid cooling system is to disperse engine fumes, pump cold air over the hot water, cool the external surface of the engine, drive airflow when the vehicle speed is low. So there will be a radiator and then there will be a fan. If the radiator is not getting sufficient air from the vehicle motion, then this fan will start spinning. Engine overheating may be due to stuck radiator pressure cap, open thermostat, broken fan belt, excess coolant. So only broken fan belt can cause overheating. I think it is time. Just we can see in the next. Do you have any questions on the problems that we solved so far? Okay. If there are no questions, we can close the call. Thank you for participating. We will see you in the next.